Welcome to today's paper reading. Today's paper is titled, TextDiffuser-2, Unleashing the Power of Language Models for Text Rendering. This paper was published on AR14 by Jingye Chen and colleagues from KUST, Sun Yat-sen University, and Microsoft Research. The abstract outlines the primary objectives of the research, which include identifying key challenges in the field, developing innovative solutions to these challenges, and ultimately improving efficiency. The methodology employed involves an experimental approach, advanced data analysis techniques, and comparative studies to validate the findings. The expected outcomes of this research are enhancements in performance, significant cost reductions, and broader applicability of the solutions developed. Figure 1 showcases the text-to-image results generated by TextDiffuser-2. The figure highlights three main aspects: accurate text generation, reasonable text layouts, and diverse text styles. These capabilities are attributed to the strong language model integration within TextDiffuser-2, which enables the system to produce high-quality text images with varied stylistic elements and well-organized layouts. This demonstrates the model's effectiveness in leveraging language models to enhance text rendering tasks. TextDiffuser-2 introduces a fine-tuned large language model for layout planning, automating the generation of keywords and supporting layout modifications through user interaction. This model encodes text positions and content at the line level, addressing previous limitations in flexibility, layout prediction, and style diversity. Extensive experiments and user studies, including those with human participants and GPT-4v, have validated TextDiffuser-2's ability to produce more rational and diverse text layouts. In the field of visual text rendering, despite significant advancements in diffusion models, generating accurate text remains challenging. This area significantly enhances the efficiency of designers in tasks like logo and poster design. Some works leverage large language models to improve spelling capabilities, while others focus on controlling text position and content. For instance, TextDiffuser uses character-level segmentation masks for better rendering. Moving on to language models for layout generation, this field has wide applications including document formatting and image synthesis. Recent advancements treat coordinates as discrete language tokens, and multimodal models ground specific objects in images. Lastly, optical character recognition, OCR, is crucial for locating and extracting textual information from images, facilitating high-level understanding tasks. Our method uses caption OCR pairs to fine-tune a large language model for generating visual text layouts. The architecture of TextDiffuser-2 involves a two-stage training process. In the first stage, the language model M1 is trained for layout planning using caption OCR pairs and optimized with cross-entropy loss. This model can infer text and layout or determine layout based on provided keywords. In the second stage, the language model M2 is used for layout encoding within the diffusion model. M2 employs a hybrid granularity tokenization method and is trained with L2 denoising loss, enhancing the model's spelling capability and flexibility in image generation. Figure 2 illustrates the architecture of TextDiffuser-2, detailing the two-stage training process involving the language model M1 and the diffusion model. In the first stage, M1 is trained to convert user prompts into a language format layout, allowing users to optionally specify keywords. This layout, along with the original prompt, is then encoded by the trainable language model M2 within the diffusion model to generate images. M1 is trained using cross-entropy loss, while M2 and UNet are trained with denoising L2 loss in the second stage. This setup enables the generation of diverse and visually pleasing text layouts, enhancing the style diversity of the output. The model used for layout planning is fine-tuned using the Vicuna 7BV 1.5 model within the FastChat framework. The data for this fine-tuning is derived from the Mario 10M dataset, specifically using 5,000 samples. To enhance the feature space, the positions are normalized to a range of 0 to 128. The training process involves setting the learning rate to 2 times 10 to the power of -5, conducting a total of 6 epochs, and using a batch size of 256. Figure 3 presents visualizations of layouts generated by TextDiffuser-2 and TextDiffuser. The key observation is that TextDiffuser-2 produces layouts that are not only more visually appealing but also more rational in structure compared to TextDiffuser. This improvement highlights the enhanced capabilities of TextDiffuser-2 in generating aesthetically and functionally superior layouts. Figure 4 presents visualizations of text-to-image results, comparing our method, TextDiffuser-2, with existing models such as SDXL, PixArt Alpha, Ideogram, DAL3, Glyph Control, and the original TextDiffuser. The figure highlights that TextDiffuser-2 excels in automatically extracting keywords from prompts to ensure accurate text rendering. Furthermore, it demonstrates a significant diversity in the fonts generated, surpassing the capabilities of models that rely on character-level guidance. This comparison underscores the aesthetic and functional superiority of TextDiffuser-2 in handling various text styles and layouts, particularly in scenarios requiring handwritten or diverse font presentations. Figure 5 illustrates the diversity in generating multiple images from the same prompt using TextDiffuser-2. This method excels in producing more artistic fonts compared to other models. Additionally, it shows increased diversity in the positioning of characters within the text and the inclination angles of the text lines. These features highlight TextDiffuser-2's capability to create varied and aesthetically pleasing text images. Figure 6 presents a comparison of the text and painting task between TextDiffuser-2 and TextDiffuser. The key observation is that TextDiffuser-2 is capable of generating text that is more coherent and visually appealing. This improvement is attributed to the more flexible and painting process of TextDiffuser-2, which does not rely on a character-level segmentation mask, unlike TextDiffuser. The figure visually demonstrates the enhanced performance of TextDiffuser-2 in maintaining the integrity and readability of the text during the in-painting process. Figure 7 presents the visualizations of operating layout through multi-round chat interactions and the corresponding images. This figure demonstrates the experimental results showcasing the ability to manipulate the layout through multiple rounds of chat, which is a novel approach enabled by fine-tuning a language model based on a chat model. The visualizations provide a clear representation of how the layout changes with each round of chat, highlighting the interactive and dynamic nature of this method. Figure 8 presents visualizations of the text-to-image generation with template task using TextDiffuser-2. This task involves using existing OCR tools to extract text information from a provided template image, such as printed, handwritten, or scene text images. The extracted text is then directly fed into the diffusion model as a condition, thereby eliminating the need for layout prediction from the language model M1. The figure showcases several samples demonstrating this capability, highlighting the efficiency and direct application of TextDiffuser-2 in generating images from text templates. Figure 9 presents visualizations of images generated without text using TextDiffuser-2. This experiment was conducted by omitting text guidance and generating images from 10,000 randomly selected prompts from the Microsoft Cocoa dataset. The results were compared with those generated by SD 1.5. Despite being fine-tuned on domain-specific data, TextDiffuser-2 maintains its generative capabilities in the original domain. The FID score for TextDiffuser-2 was 24.06, compared to 23.03 for SD 1.5, indicating a slight increase but overall minimal difference in quality. Table 1 presents the results of ablation studies focusing on the amount of fine-tuning data used for the language model M1. The study includes various data amounts ranging from 0K, 2-shot learning, to 100K. Key metrics such as accuracy, ACC, precision, recall, rec, and F-measure, F, are reported. Notably, the 5K data setting shows improved performance over the 0K 2-shot setting, indicating the benefits of additional fine-tuning data. The table also highlights consistency in metric presentation across subsequent tables, omitting the percentage sign for clarity. Table 2 presents a comparison of OCR accuracy using different tokenization methods on the MarioEval benchmark. It highlights that the accuracy of the center and LR settings declined significantly by 22.39% and 29.26%, respectively, compared to the LTRB setting. Additionally, the table shows that subword-level tokenization significantly underperforms character-level representation, with a 42.1% decrease in accuracy. This method also makes the model insensitive to the spelling of each token, which poses challenges to the text rendering process. Table 2 presents the results of ablation studies focusing on the representation of coordinates and the level of tokenization used. The study differentiates between char, which tokenizes keywords into individual characters, and subword, which uses byte pair encoding (BP) for subword tokenization. The table highlights that using the top left and bottom right corners for representing text lines, combined with character-level tokenization, leads to superior performance in terms of accuracy. Conversely, single-point representations, such as using the center point, result in a significant drop in OCR accuracy, as evidenced by a 20% decline compared to the top left and bottom right setting. This suggests that the choice of coordinate representation and tokenization level has a substantial impact on the model's ability to accurately render text. Table 3 presents the quantitative results and user studies conducted to evaluate various text-to-image models. The table includes metrics such as FID, CLIP score, OCR accuracy, and user study scores for layout aesthetics, style diversity, text quality, text-image matching, and in painting ability. TextDiffuser-2 is highlighted for achieving the best results in the majority of these metrics. The incorporation of GPT-4v in the user studies is also noted, with the best and second best results marked in bold and underlined formats respectively. TextDiffuser-2 demonstrates significant capabilities in generating diverse images while maintaining the accuracy of the text. It has applications in enhancing creativity in fields like graphic design and educational materials. However, it faces challenges with complex languages, potentially leading to few-shot or zero-shot scenarios. Additionally, there is a risk of generating images with false text information if used maliciously. Future work will focus on improving the rendering of multiple languages and enhancing the resolution of generated text images, as well as addressing robustness issues with overlapping layouts. Figure 10 presents the cumulative distribution function to analyze the length of composed sequences. It highlights that 94% of the samples have a composed sequence length less than 128, and all samples are below this threshold during evaluation. The figure also notes that increasing the maximum length to 256 would accommodate 99.2% of training samples, albeit with increased computational costs. Figure 11 presents additional visualizations of layout predictions. The specified keywords are highlighted in blue in the first two rows. The language model demonstrates its ability to organize these keywords, placing related ones in the same line and generating visually appealing layouts. Notably, the final row of predictions includes substitutions not present in the original prompt, such as 200G for 200 gram, showcasing the model's logical interpretation and flexibility in layout planning. Figure 12 presents visualizations of text generation guided by single-point conditions, specifically the center point and the top left point. The prompt used is a text image of hello. The last row of samples, highlighted by red boxes, indicates instances where the rendered text is incorrect. This figure demonstrates the challenges and inaccuracies associated with single-point supervision strategies and text generation tasks. Figure 13 illustrates the process of generating text images with various angle conditions. Specifically, TextDiffuser-2 is retrained to incorporate 181 angle tokens, spanning from -90 degrees to 90 degrees. In the language format layout construction, the angle token is positioned after the 4 coordinate tokens. The results demonstrate that the generated images accurately reflect the specified angle instructions, showcasing the model's capability to handle and apply angle conditions effectively. Figure 14 presents a comparison between TextDiffuser-2 and 2 other models, the Character-Aware model, CA model, and GlyphDraw, using samples from their respective papers. The figure highlights 4 samples for each method, demonstrating TextDiffuser-2's superior rendering accuracy over the Character-Aware model, which is noted for its typographical errors such as missing letters and incorrect spellings. Additionally, TextDiffuser-2 is shown to outperform GlyphDraw by its ability to render images with multiple text lines. The comparison also notes the character-aware model's reliance on larger language models for enhanced text rendering, contrasting with TextDiffuser-2's effective use of a smaller-scaled clip text encoder. Figure 15 presents comparative visualizations of generation results using overlapping layouts. The key highlight is the enhanced robustness demonstrated by TextDiffuser-2 compared to other methods. This figure serves to illustrate the effectiveness of TextDiffuser-2 in handling complex layout scenarios, providing a clear visual comparison of its performance against alternative approaches. Figure 16 presents a comparison of TextDiffuser-2 when trained with different versions of the Stable Diffusion model, specifically SD 1.5 and SD 2.1. The results show that the model based on SD 2.1 provides more detailed and accurate renderings, especially for characters with smaller sizes. This enhancement is attributed to the stronger power and higher resolution of the latent space in the SD 2.1 model. The visualizations clearly demonstrate the superiority of SD 2.1 in capturing intricate details and maintaining clarity in small-scale text, highlighting the potential for further advancements in text rendering technologies. Figure 17 illustrates the capability of TextDiffuser-2 to generate text that accurately aligns with quadrilateral bounding boxes. This demonstrates the model's proficiency in adhering to geometrical constraints specified by the boxes. The figure showcases various examples where the text is precisely positioned within the quadrilateral shapes. For future enhancements, the plan includes increasing the number of control points to allow for more artistic and complex text renderings. Figure 18 presents the structure of user studies conducted in the research. The studies are divided into 5 key questions, each focusing on different aspects of the system's performance. For questions related to layout aesthetics, style diversity, and in-painting ability, users are required to make a single selection. Conversely, for questions concerning text quality and text-image matching, users have the flexibility to choose multiple options. This approach ensures a comprehensive evaluation of the system's capabilities across various dimensions. Figure 19 illustrates the process of conducting user studies using GPT-4v. The figure showcases how GPT-4v is prompted to proceed step by step, deriving final answers through logical analysis. This method highlights GPT-4v's impressive literacy skills and the reasonableness of its logical chain. The dialogue record in the figure demonstrates the effectiveness of this approach in user studies. Figure 20 illustrates the process of conducting user studies using GPT-4v. This figure is the second part of a 2-page document that details how GPT-4v is employed to gather user feedback and evaluate its performance in various tasks. The study involves presenting users with images and questions, and the responses are analyzed to assess the capabilities of GPT-4v in understanding and generating content based on visual inputs. This methodology helps in refining the model and improving its usability in real-world applications. Thank you for watching.